Have you ever wondered how Linux manages memory? It's a fascinating process that plays a critical role in ensuring optimal system performance and resource utilization. At the heart of this process, we have memory management. Memory management in Linux encompasses several key aspects. It begins with virtual memory, a system that manages physical RAM and swap space, providing an efficient way to allocate memory and protect processes from accessing each other's memory. Then we have memory paging and swapping, where Linux moves inactive memory pages to the swap space on the disk to free up physical memory. Add to this the page cache, a feature that caches frequently accessed data from the disk in memory, thus improving I/O performance. We also encounter memory allocation, memory zones, memory ballooning, transparent huge pages or THP, memory compression, the out-of-memory or killer, and memory profiling and tuning. Now that we've set the stage, let's dive deeper into these key areas of memory management in Linux. First up, let's demystify the concepts of virtual memory and memory allocation in Linux. Virtual memory is a clever technique used by Linux to manage physical RAM and swap space. This allows processes to see a virtual address space instead of the actual physical memory locations. The kernel maps these virtual addresses to physical memory, making memory allocation more efficient and protecting processes from intruding into each other's space. Now, how does Linux allocate memory dynamically to these processes? It uses techniques like demand paging and copy on write. In demand paging, the kernel only loads pages into memory when they're required, reducing unnecessary consumption. Copy on write, on the other hand, allows multiple processes to share the same page until one needs to modify it. This allocation is managed by the kernel's memory management subsystem, which includes the buddy allocator for physical memory and the slab allocator for kernel objects. With a grasp on virtual memory and allocation, we can now explore memory paging and swapping. How does Linux handle a full physical RAM scenario? The answer lies in memory paging and swapping. When RAM fills up, Linux uses a strategy called swapping to make room. It moves inactive memory pages to a location on the hard disk known as swap space. This frees up RAM for active processes, but while swapping ensures your system keeps running, it can slow things down if overdone. That's because accessing data from the hard disk is much slower than from RAM. So, how does Linux minimize disk reads? Enter the page cache. This is a clever system that stores frequently accessed disk data in memory. When a process needs data, it first checks the page cache. If the data is there, great. This is called a cache hit. If not, it's a cache miss, and the data must be read from the disk. The page cache is dynamically managed by the kernel, ensuring optimal performance. Up next, we'll delve into memory zones, ballooning, and transparent huge pages. Linux's nuanced approach to memory management extends to memory zones, ballooning, and transparent huge pages. Diving into memory zones, Linux cleverly divides physical memory into distinct zones like DMA, normal, and high mem. Each zone, with its unique characteristics, caters to different uses and has its own memory allocation policies. Now let's float to the concept of memory ballooning. This technique comes into play in the world of virtualization. Think of it as inflating or deflating a balloon driver within the guest operating system. The purpose? To dynamically adjust the memory allocated to virtual machines based on the demand. Lastly, we have transparent huge pages, or THP. This Linux feature is a game changer for memory-intensive workloads. It allows the kernel to use larger page sizes like 2 megabytes or 1 gigabyte for memory allocation. This reduces overhead and boosts performance. Finally, let's talk about memory compression, the killer, and memory profiling and tuning. To wrap up, we'll look at memory compression, the killer, and how to profile and tune memory in Linux. Memory compression, with features like zwap or zrom, squeezes memory pages in RAM to reduce usage, thereby enhancing performance. It's like stuffing more clothes into your suitcase by rolling them tightly. Next, we have the out-of-memory or killer. This is Linux's last line of defense against system crashes due to memory exhaustion. Imagine it as a bouncer at a club, deciding which processes have overstayed their welcome when the place is packed to the brim. Lastly, let's talk about memory profiling and tuning. Tools like Free, Top, VMstat, and SAR help monitor memory usage and identify performance bottlenecks. By tweaking kernel parameters or application settings, you can fine-tune memory usage based on your workload characteristics. And that's a wrap on memory management in Linux. We hope you now have a better understanding of how Linux optimizes and manages memory for optimal performance and resource utilization.